So again, we want to welcome everyone that's decided to visit with us today. We are here today to, as you can see on the PowerPoint slide, explore STEM connections with Tetrix Prime. And we hopefully, through the course of this next hour, you'll get kind of a good idea of not only introduction to Tetrix Prime, but also begin to look at STEM concepts and products that we use every day in a little bit of a different way with that. So we're going to start out with some introductions so you kind of know who you're dealing with from a lot of different levels. Starting with who we all work for. We are employees of Pitsco, and for those of you that don't know Pitsco, Pitsco is an educational hands-on company that's been around over 40 years now, and it started with teachers. Three industrial arts teachers who are passionate about what they did, and the students that they worked with were frustrated with being able to supply hands-on components to their kids in their classrooms. So one day they were looking at each other and said, we could do a better job of this. So out of their own garages, with a very small startup, they formed Pitsco. And after over 40 years, we've got over 200 employees, the multi-million-dollar company, and we service not only the United States, but we've got customers that are global in nature. So, but we've always maintained our identity as an educational company. That's our priority. Those of you that are familiar with us know that that's a priority for us. Our vision statement is to obviously lead educational change that positively affects learners. That's something that we really take to heart and we live by. We gauge our success as a company on the number of students that we serve and that our products reach out and touch on a daily basis. So that's kind of who Pitsco is. And as far as the rest of us, and again, you can kind of tell that we're not afraid to laugh at ourselves, but my name's Tim. I've been with the company about 13 years.
We should all put our heads together.
Yes.
And see if we look like the three on screen.
Yeah. My background with the company is that the last 12 years I've worked with customer service and technical support for the Lego Mindstorms side of the joint venture that Pitsco had with Lego. So that's my introduction to robotics and my background and why I'm kind of here today with this. And prior to that, I was with spent the early part of my working career with manufacturing in a kind of a blue collar role. So, and then with me today, I've got Ray.
I'm Ray. I'm a former industrial arts teacher from Lamar, Missouri, and I've been with Pitsco now about 10 years. And I have been involved in a lot of the writing of some of the curriculum activities that we do, and the builder's guides and setup guides, the things that the teachers need to use in the classroom with the Tetrix Prime building system.
Okay, and then also we have Ruthie. She's kind of the brains of the operation, by the way.
Brains?
Yeah.
Hi, I'm Ruthie. My background also is in education. I taught. Prior to coming to Pitsco, I also did mental health with middle schoolers and high schoolers, which is why I work so well with these guys. I, again, have a background in education. I've been at Pitsco for 7 years. And prior to joining the marketing team, I worked in the teacher education department.
Okay. So again, you can see that as a company, and not only as a company, but the employees that make up the company have very strong ties in the past and in the present at the education world. And for those of you that are young enough not to recognize the picture referenced on screen, the only thing I can say is check out the Netflix and some of the old TV Land and stuff. You'll get a kick out. You'll get the joke.
I used to have a haircut like that once in high school, I think.
Mine kind of looks like that now.
And you can see mine's going away, so that's why I have no guy in the middle. So that's to go with that. So they said the head is too fat to be on Tim. Are you well? You can probably get some argument for that, but we'll go ahead and go on from there. Today's goals for the webinar. And again, I want to make sure that everyone that's online feels free during the course of this. Everyone is muted, so we won't be able to hear your questions, but please feel free during the course of this. If you have a question, if you have a comment that you'd like us to discuss or bring into the area, please type that into the chat area. Not everyone else can see what you type in, but we will be able to see it here, and we will be able to hopefully respond to it. If it gets coming in a little bit too fast, too furious, Ruthie is going to try and take notes, and then we'll respond back. If we can't get a verbal response or audio response, we'll go ahead and try and type that in a little bit later. So with that out of the way, let's talk a little bit about, again, the goals for the webinar. We do want to introduce to those of you that are new to this, Tetrix Prime, and what exactly it is as a product, and how it came about to be, and why we want to talk about that in relationship to STEM. And we also then want to kind of, again, get everyone to really begin to think maybe a little bit about STEM in a slightly different way that we found to be very effective here at Pittsco, and when we talk to teachers about STEM, and then basically just what STEM is as a conversational piece, because for some of us might not recognize that. And then finally, how you can bring the two together, how we can actually make STEM connections with Prime, and why you might find it useful in the classroom in relationship to STEM and teaching STEM. So with that being said, we need a Shemp. Well, that's true. We probably do need a Shemp that would round out the Stooge environment. So let's go ahead and let's move on a little bit to the next slide. So you're probably wondering what this is all about, and what we found as a good way to kind of change our thinking about STEM is to kind of look at maybe an everyday object and really try and identify how that might have a connection to STEM. And before we do that, let's talk a little bit about STEM just in general, because there's probably a lot of different views when we talk about STEM, in that what is the relationship of STEM as far as what it actually means. Some folks, it's science, technology, engineering, math, and other folks have a strategy that engages the mind is one of the things that some folks, that when you think about the acronym of STEM. So some people think STEAM, some people think STREAM. I mean, there's a lot of different viewpoints on this, but here at Pittsco, one of our kind of outlooks that when people throw out the word STEM comes to mind, that we're really talking about hands-on activities that engage across multiple disciplinary areas of study and bring them all together, and through that hands-on activity create a much stronger experience that really brings out the strengths of all the different disciplines.
All the disciplines, ties them all together.
Yeah, so that's kind of what, when we're talking about from Pittsco, that when we mention STEM, that's kind of what we're coming from. That's our viewpoint. So with that out of the way, let's get back to what's up with the pencil. And so what we found that can be very effective is when we think about everyday objects, sometimes we don't think about them in the viewpoint of STEM. So we've created what we call a little graphic organizer that kind of allows us to kind of look at this and break it down in a very unique way. So we're going to start throwing out a couple ideas about how we might look at STEM, and we hopefully the idea is that some of you, as you begin to look at this in a different way, will begin to provide some ideas too, so this becomes a real dialogue with everyone that's out there. But you'll see there's 4 different main areas in this grid: science, technology, engineering, and math, of course. And then there's this center area, because truly there are a lot of overlap in some of these areas where we begin to talk about this, where you might have one idea that actually hits several areas and overlaps. So I'm going to start with Ray. So Ray, if you were thinking about a pencil, what would be the first thing in relationship to STEM that would come to mind?
One of the things that comes to mind immediately to me is, in science, the material science of the makeup of the material that you write with.
Okay, so you've got a certain composition to a pencil. You've got wood, you've got graphite, you've got the composition of the eraser on the end. And that all is a part of our science, right? Science world, what composition of materials, that type of thing. I look at it and I see there's an obvious shape to this pencil. It's an octagon. So we can begin to look at that in the aspect of a math type of a relationship,
shapes.
right? We've got geometry and math involved with the number of sides and the type of shape that it is. Ruthie, anything that you think right off the top of your head when you look at a pencil?
Well, when I look at a pencil, and I think that students do the same thing, you can tell students this is technology. A pencil is technology, and they'll completely disagree with you because they think technology is iPads and smartphones and computers. But really, this is one of the first writing tools. And so the evolution of writing tools could be discussed for technology.
So you could have a very rich discussion just with the idea of from a technology standpoint, the evolution of writing and where it all began and when we started to document things and how we documented things and what that meant as far as the type of tools that it took to actually begin documenting, whether it was drawing on a cave wall or using a pencil or an ink quill or however we began to do that. You can begin to start having a rich discussion about that in regards to technology.
We do have a question that says, why wood for science? Most of the time, science is thought of in the natural world. So even though it's a pencil, we could talk about different types of wood in the natural world to relate more to the science realm.
Okay. So
we could also talk about, is it wood or is it wood composite? Is it built up out of wood fibers, wood waste, or are they using regular sections of wood?
Right. So there's not only that there's also the technology of what it took to actually create that pencil, right?
Right.
The manufacturing aspect of it and why it would the machines that it takes to actually produce pencils and the engineering that goes behind the design and why do they make pencils a certain length or a certain thickness and the shape. From an engineering perspective, does it make more sense to be round or the hexagonal shape? And the things that begins to come into play. So, does everybody kind of begin to get a little bit of the feel on what we're going to try and do today in regards to the way we look at the Tetrix Prime and the way that we want to kind of relate that back to STEM? We want to really kind of reinvent maybe the way that we look at our products and how we kind of make that STEM connection.
And to also note that something as simple as a pencil can have the connections across science, technology, engineering, and math, and some of them might overlap. Engineering, in my mind, is encompassing of science, technology, and math. So part of engineering kind of runs into all of them. That's why I kind of put even manufacturing. The manufacturing of a pencil includes science, technology, math. So engineering is the section that I always think of is all encompassing of the science, technology, and math, and even arts.
Yes, and that's why we've got that gray, that center area that really kind of graphically represents that overlap and the way things kind of connect together.
Ooh, very good point. Pencils allow mistakes, and this puts emphasis on the approach of engineering. So that's a very good point. Making mistakes is a big part of learning.
Very, very big part of engineering also.
And even in the fact of writing graphically on the internet. And but that's why we've got erasers on mistakes, right? Or on pencils, and that allows us to the freedom of feeling like we can make a mistake and go back and learn from that. Everyone probably really knows that effective learning sometimes really comes from the mistakes we make, not the successes as much.
Sometimes the error learn more.
Okay. Good point. Very good point. So let's kind of move along and kind of take this into the next level. And this is kind of what people probably would more traditionally think about when we begin to talk about STEM ideas and technology. And we've got a picture here of some gears. But we can take that same thought process that we applied to the pencil, and we can then begin to look at the other aspects. And that's another good point that somebody has brought up, of mass production of identical items and what it takes to bring that about. But and that could apply to this slide as well when we begin to look at this in regards to that same kind of a format. We've got gears. Obviously, this looks like metal gears, but gears of different sizes and different teeth configurations and things like that that are meshing together. So again, in that same type of a vein, we can begin to look at that in this slide of this STEM graphic in this organizing chart, and we can say, for me, again, when I look at that, I look at the size and the shape of the gear and the number of teeth, and I begin to see some really strong math connections with this that kind of not only are in math, but also kind of cross over in some of the other areas as well, as far as ratios and gear configurations and the way that they relate to each other.
You can also talk about the science behind the metallic alloy used to make up the gears to reduce friction. You change that alloy and maybe have a lower friction, longer lasting gear. You can talk about lubrication.
So the materials that are involved in the manufacture of the gears, and what the composition of an aluminum gear versus the steel gear, and the weight that brings into play, and the function that then how the weight impacts. There's a lot of things that you could begin to talk about that. And again, some of these concepts are going to, again, apply whether it be a pencil or the gears. We can, again, go back to the mass production of virtually identical items. How does technology impact the creation of gears, and what does it take to actually build that gear? Multiple gears, how are they made? Some of those things, again, when we start to think about them, can really begin to overlap.
In the engineering side, the gear system itself, worm gear versus spur gears.
Right. Someone made a comment about mechanical transmission possible with gears. Again, really hitting that engineering area and then crossing over into some of the other aspects of being able to, what's it take to design a transmission and have that work successfully, and from an engineering standpoint. And there's size, transmission, and then what it's got to go into and what it's got to actually perform, and all kinds of things.
Whether it shifts smooth or not.
Shifts smooth. There's a lot of aspects that you begin to have to think about when you create a transmission. My background from the production years, I worked in a heat treat facility that had this huge furnace that was half a block long, and it was driven by a small 3-horse motor, but the transmission on it was huge to gear it up and actually drive the drive on this furnace. So that aspect of gears and things can really impact a lot of things. What was the one about the building system? Go back up just a minute there.
Oh, the question was if these are the gears in the Prime building system.
No, unfortunately they're not. But now we do have gears in the building system. So that when you begin to look at that, you can again begin the discussion of gears, because concept-wise, that part doesn't change. The laws of physics don't change, and the way things interact don't necessarily change. So that's one of the beauties of robotics, and the way it applies to this is that you can give kids that exposure to an activity and a material that is very real world in the way that it treats the subjects that maybe are outside of their scope. So a NASA scientist is going to treat a gear the same way as a NASCAR technician, or someone that's in a design firm for computers and stuff like that. So when you're giving kids exposure to this type of material at the level that they're at, you can begin to know that the gear is going to react the same, whether it's with them in the classroom or someone else in a different environment. So
Correct.
That's one of the beauties.
All right. Ready to move on?
Yes. So Let's now, after we I think everybody should have a little bit of an idea where we're going to try and go with this. Let's go ahead and move on and talk a little bit about what we're here to talk about, and that's Tetrix Prime. And we have to start that process with kind of how it all came around to be. And for those of you that don't know, Tetrix actually was created back in 2008. And we, at that time, started with just one product, and it was called simply Tetrix. And the reason that we created it was because the U.S. First Corporation came to Pittsco because of existing relationships, and they said, we need a platform, a building system that's appropriate to our competition that they had in mind. And they had a very specific list of requirements for that product and what it needed to do. But one of the main aspects of it was that they needed a very robust system that allowed students to build in a realistic scale that was very strong and very up to the challenge of competition. So that's how we came to actually create Tetrix Max. And we've got, I believe, a slide to kind of show an example of what Tetrix Max or Tetrix kind of looks like. And to be honest, it fit that role very well. It's a very robust system, and it worked really well in that competition type of setting. It worked so well that people began to use it for other things, and it began to go into the classroom and began to be used by the hobbyists and things like that, because of the way that it worked. But when we started to kind of repurpose it, there was some things that we found that were lacking based on feedback from people that were using it in the classroom. And we began to, Pittsco's always been very responsive to listen to that feedback. And here's a shot of an idea of the scale. This robot's over 5 foot tall that you can build with Tetrix Max. And I think we have another shot where we actually duplicated the Mars Curiosity rover in Tetrix Max. So you can begin to get an idea of the scale that you can actually build with the Max. But when we began to bring it into the classroom, there was some shortcomings as far as how it really worked with a teacher's needs in the classroom and the restraints or constraints that a teacher was working under. Still worked very well for competition, but in a classroom everyday setting, it had some shortcomings. So we began to listen to some of those, and over the course of the feedback, we really decided that to address those questions and those shortcomings, we really needed to come out with an addition to Max, and it became such of an encompassing addition that we actually created a new product out of it. And so we created what we called Tetrix Prime. And let me start off by saying that it is very much on the same hole pattern as Tetrix Max. So for those of you that have experience with Tetrix Max, this is going to be, you can look on this as like a huge addition of new parts that will work with what you already have. So, and for those of you that are not existing users, you can kind of look at it as a starting point to not only working with it by itself, but also then later on down the road, if you wanted to add Max to it, you could, because it all is designed to work together. And one of the things, again, from the idea of a starter set, it truly is that as a starting point. It begins to address the needs of a teacher that wants to get into a classroom and immediately begin to use a product as quickly as they can, because obviously time is of a big concern to a teacher and how they maximize their short class periods and getting the most out of those. That was one of the major points of feedback. So one of the things that we really concentrated on with the advent of Prime was being able to maximize the time a teacher had in a classroom. And so all of the builds, all of the basic functions of the way the robot is used is designed around the idea of making this easier for and more accessible and quicker for the teacher and students to build robots and really get onto the major aspect of using this in the classroom. One of the big points in that is our patented quick rivet system. This is kind of one of the key things that we've got with the Prime set that still has the strong metal component with the aluminum beams, but we've added plastic preformed pieces as connectors and brackets, and then this quick rivet system that allows the very rapid prototyping of putting things together, evaluating them, and then taking them apart and making changes and making that an effective part of this engineering process. So that's the quick rivet system. And to kind of demonstrate that, Ray and I are going to do a little bit of an exercise. I've got, if we want to go back to the webcam or maximize the webcam, we have got in front of us a set of Prime pieces, and if you kind of look, there's really not a lot of them here, but what I'm going to try and do in the next few minutes while Ray and I are going to have a little bit of a conversation in the course of this is I'm going to actually try and build one of the robots that we suggest with the built online. So what I want everybody to do, though, is kind of note, because again, time is a huge part of a teacher's, just kind of keep an eye on starting time, how long it takes for me to get finished, and we'll kind of then talk about that as at the end as far as whether or not it's we think it's going to be an actually improvement. So with that being said, I'll go ahead and start. And Ray, who was actively involved in the development of this as a product and curriculum, what was some of the things that you were thinking about, in addition to what we've talked about, that when you began to create this as a product?
One of the things that when we started building this product and developing this, we wanted something that students could put together quickly so they're not spending all their class time working on building a robot. We want them to build a robot that they can do something with. We want them to actually do something.
Okay.
Once the robot's built, they need to be able to make changes to that robot quickly and easily, and they need to be able to do some activities. So as we developed this, we came up with a builder's guide. And the builder's guide and setup guide that come with the set. Setup guide gives the teacher some instructions on how to pre-assemble the gripper so that students don't have to spend their time building the gripper. It can just attach quickly. We show some basic techniques of how to build with the Prime parts. And then we show 3 different hero models that can be used right out of the box. Everything that you need to build those is in the box, and it also has some scientific activities that you can do once you have that robot built.
So again, that was one of the feedback things that we got from teachers is they didn't want to feel like that it was a sink or swim situation, right? They wanted to feel like that there was some support when they got this, and right out of the box they would be able to get going in a very smooth manner and not feel like they were just stranded, right?
Right. And once you give students an idea, a starting point, they'll take off with it. And so we're giving students and teachers a starting point for them to go from, and then they can go to the moon with it.
Okay, again, and going back to the idea that reoccurring theme of a starting point of an idea that this is not necessarily the only thing that you can do with this, but it's definitely a beginning. And that part of that process, that engineering and scientific process, is that you're gonna try something, you're gonna evaluate it, and then upon reflection, you're gonna potentially make changes and improvements.
That's engineering, whole engineering process right there. Being able, and the fact that it's done with the quick rivets and thumb screws and only one tool. We need a hex driver to tighten up some set screws. Other than that, we don't have to have a lot of tools and equipment to keep up with. And so students can quickly change and make modifications.
Okay.
And try something new.
Okay. And that was based on we actually, again, this is an international product in scope. So one of the things that we had to address, there are some cultures that look at the idea of tool use being exclusively in the realm of the male type of people. Mm-hmm. And we know that there are engineering opportunities and abilities from females that are just as good, if not better, than some males.
You're right.
So this helps address that idea of you don't have to be a huge tool user to be able to use this system,
That's
right?
right.
You do have to work a little bit though. So you can see this is going together fairly quickly.
One of the things that we wanted to do is for students to be able to get in there and do something with it. So we wanted to build a robot or design a robot and a system that they could change things quickly. And so the prime stuff being snapped together, a lot of it with the quick rivet, makes it quick to change. And the lengths of the beams, we can use some math on those because the length of the beam is the hole pattern. We count the number of small holes to determine the length of the beam. And so we can use those and we can add those together and take shorter pieces, add them up and to get longer lengths.
Okay.
And we have connectors that do that.
Now, and you can tell, obviously, I'm not going by directions, and I've done this before, but one of the cool things about this, again, as a product is the fact that, right, if I happen to put this in a little bit different place, that's probably not going to prohibit this from working, right?
No,
I mean,
not-
we're going
not
to
at
be
all.
able to actually still have a functioning robot if I've got this battery connector a little bit in position differently
Right.
from.
And
one
maybe you
person
want to
to
move that. Maybe some process that you're using, it needs to be in a different place
Okay.
than what the original instructions, again, are starting point. So this gives you a location you can put it. You could reposition that battery to some other location if you wanted to.
And for those of you that are wondering, what I'm attaching right now is a wireless receiver. So we have a 6-volt battery source that you can see, and I've got a continuous rotation servo here. I've got a standard servo there, and then when I attach this 6-volt rechargeable battery to that wireless receiver, the set comes with a gamepad, and you see that I've just made a connection, and we now have steering, and we have a moving robot. And I don't know if anybody
And that took you 6
watched the
minutes.
times. 6 minutes. Okay. So you can see hopefully that we've got a product that will maximize again, the teaching time that a teacher has to actually with building. We know that there's value with building. We don't debate that at all, but we know that the teacher doesn't want to spend all their time with just building. So that's an idea of how quick the robot goes together. You can see we've got strong aluminum pieces. We've got plastic components. And where would be somewhere you would go with this from a starting position, Ray?
Now that we've got a robot built, let's take that robot and use it to let's count the rotations of this shaft.
Okay.
And we can do that. There's a set screw on there. It makes it easy to locate where that set screw's at. Let's make it rotate one time, and let's see how far it travels.
Okay.
And that's based on the circumference of this wheel.
Okay. So
we've got math, and we've got engineering.
Okay. Don't get in that too quick because we've got our graph that we're going to go over with a little bit to begin that. But hopefully everybody can kind of begin to see that we don't have to look too far with this that really to begin to make our connections. And before we go any further, I want to go ahead and point out too that this is, again, from that theme of a starting point. This is RC. This is remote control. Everything that you see here comes in the set. You should be able to get this up and going again under 10 minutes easily,
Yep.
and you've got a moving robot. But I said just then robot. Is this actually a robot, or is it a remote control vehicle?
It's a remote control robot.
Okay, so you can see that Ray's in the business of splitting hairs, but the idea is that there probably is a very thin line that's becoming thinner or maybe wider is what we say, and it's graying about the fact that where does RC start and where does robotics start and where do the two mix. But for us here, we think it's a very easy beginning, and then when you want to take it to that next level of autonomous type programming, you've got a lot of options, don't we, Ray?
Right.
We can actually take this system and if we want to make it full autonomous, for those of you that are used to using the Lego, we can actually create Lego robots. So I'm going to set this out of the way just for a minute so we can show some of these others. And for those of you that recognize Lego, You can see that this is the latest Mindstorms controller. This is an EV3 brick. I've got the same metal substructure here, the prime components and motors, but I've got the EV3 brick. I've got a mind sensor module that you can add to this that gives this brain the ability to control these servos. And then I've got the output, the 6-volt output that provides power to that. So with very little effort, you can actually adapt this and really expand the use of your Mindstorms, because now all of a sudden I can take this to a whole different level where I can build a very strong substructure, including Max components, because of the way that Prime will interact with Max, and then begin to expand on top of that with elaborate Lego constructions that take advantage of the Lego construction as a part of that, and really grow this as options that you have with the robot.
We have a couple of questions.
Okay.
Would students be able to create their own RC protocol?
Potentially, yes, depending on how you would do that. Now, what we've done is we've created a wireless receiver and a gamepad that comes shipping with the set. So that's kind of a standalone system. You could interchange the receivers with other gamepads, but that's kind of a key turn system. But if you wanted to create your own RC protocol, you could potentially, like for instance, with the Lego device, I could create a remote control from one EV3 brick, build a controller device, and actually talk to another EV3 brick and write code to create an RC protocol where this unit would control this one. So you definitely could do that. So good question. And if you didn't want to do Lego, if Lego is not your thing and you want to expand a little bit on that.
Before you get away from this Lego, let's talk about that Lego connection point.
Okay.
There are several questions about the Lego.
And that quick rivet.
Okay.
That quick rivet, how that quick rivet works.
Gotcha. So how are we connecting the two? So what we've done, and I hope everyone can see this because this is one of the beauties part of the system. I've got a standard Lego connecting peg. And if I look at the connector peg that I've got from the Tetrix Prime system, you can see that they're very similar in size and shape. I know that's a little bit distant to see, but hopefully you can kind of tell that. And what we've done is we've taken out where I would use the Tetrix locking pin. I can take that out and I can replace that with a Lego 3-module connecting peg. And then the Lego components, a standard Lego component, I'll take this apart just for a minute, will just snap right on there. And now I've got a Lego connection point. And as long as I maintain the spacing provided by a prime metal element and a plastic spacer beam there that these quick rivets require, I can actually build in all 4 directions off of these metal elements with Lego, and it all maintains the same hole geometry and the spacing. So you can see that I can build Lego device and I can simply just snap it right onto my metal device, and it snaps right on, and I've got a very robust connection that takes advantage of the strengths of both, and I've got good options here.
Do we have information on our website? One of the questions is asking about adding the EV3 to the Tetrix Prime.
We've got a little bit, and we've got more coming. One of the things that we want to make sure that everybody is kind of aware of is that Prime has been out now 6 months, a little bit longer than that now, 8 months. And as a new product, we really are beginning we created a new website, tetrixrobotics.com, that we'll give access to and links later on. But we are really trying to populate that website with build ideas, information on how to go ahead and really take advantage of all of the resources that are available with the new product, and how to build with building ideas, ideas on where to get product and how to put them together and add them to, and go from there. So that's coming in more and more all the time.
Okay, one other question we have is, are Tetrix devices such as servo connections compatible with Legos Brick?
Well, through this Mindstorms module, they would be. And that's the key, is you have to have some kind of a way of translating connection-wise between a standard servo connection, which these are standard hobby servos, and the way that they connect to interface with this. And this is a module that is we actually now are going to sell it on the Tetrix Prime, the Pitsco website. So you can actually get this from us, or you can get this from the manufacturer, mindsensors.com.
Can we zoom in on that? Someone has asked if we
If
can zoom in.
I'll help you move that over. But that's called it's a mind sensor module. And Ray's going to point at it there, and it outputs to 8 different servos. It actually uses as a power source, again, the Prime 6-volt power source. But if you connect that, again, there's a free downloadable block that goes right into your EV3 software, your Mindstorm software. So you don't have to change your program. You can actually program right in Mindstorms, and you can control your standard servos, whether it be a continuous rotation servo or a standard servo that's 180 degrees.
Okay. It says they showed the mechanical connections. How does the EV3 control the Prime motors?
Through this module. So I've got this module connected to a sensor port, and when I access that in my EV3 software, then I can send commands just like would anything else connected to the Mindstorms to control that servo. There's again a downloadable block that's free. You don't have to pay for the block. You just have to get the little connection point and add it to your robot, and you can control those outputs, those servos. You could do that with a Max servo as well. You would just have to change your power source.
All right.
So again, we've talked about if you're a Lego user, but there's other users out there, right? So
Right.
Let's look at some of the other options we've got real quick before we talk more about our STEM concepts. This is an Arduino.
Now, remember, the Prime system is a building system. So the structure and what you use to control it are really not related that tightly.
Yeah.
Although the whole pattern works for the Lego thing,
Yeah.
which for those people that have the Lego is great. If you don't have Lego and you want to get involved in open source with the Arduino, we have an Arduino on here, and we are in the process of developing a shield,
Okay.
just for convenience sake.
It's this top part.
There's the top part up here, and we can plug in our servos and our battery. We have 3 sensor ports set up in it. We have a start and stop switch, and we can set this up, and now we have a Tetrix Prime wheelie bot with Arduino control.
So again, if you want to take it to that next level of autonomous from an RC, you've got a lot of options. And it's not just Arduino either.
It's not Arduino.
We could do that with
Raspberry Pi.
Raspberry Pi. We could do it with a MyRio if you really wanted to get high end with that. We could do a lot of the different controllers that are out there that are open source. Again, this is a starting point
It's a building
and
system.
a building system, and it's open ended. And as long as you've got the controller that you want, and as it can output to servos, that's the key
That's the
with
key.
the Prime components. If you wanted to go with Max, then you also would need an ability to output to 12-volt DC motors. And that ability, as long as you have that ability, it doesn't matter what controller that you use, doesn't matter what software you use.
Right.
You've got different options available to you that based on your software program of choice or your hardware controller program of choice, this becomes just a vehicle to add to that, right?
Right.
Okay. So hopefully that gives everybody a little bit of an idea of some of the potential. So let's just go in and again, take this back to STEM.
Okay.
So let's go back to our standard wheelie bot. Let's just switch this out here real quick. And let's talk about this as far as some of the ideas. I'm going to unplug my battery so I don't run it down. How we would look at that in our STEM grid. And we're going to look now on our graphic and what are some of the STEM connections. Right off the top, I'm going to go ahead and go back to what you said, Ray. You talked about this back wheel and rotations, circumference. We're hitting math big time.
Math big time right there. A little bit of pi too.
A little math and pi. So you can see from a geometry aspect, we could ask the kids to do this at a couple different levels, right?
Right.
If we're working with the younger kids, and we just want to get them to start to measure things, put a ruler down or tape measure down and a start point and an end point, and you're talking math and measurement, right?
Right.
But if you wanted to make them calculate the circumference and figure that out ahead of time.
Right. And with those younger students, you can bring this around and just count one rotation or two rotations and figure out the distance and have the students measure that distance and then determine if it takes a meter for this to go around 3 times, how many rotations would it take to go 20 meters?
Okay, so now we can begin to work with the old distance and speed formula. Speed equals distance over time, right?
Right.
And we can begin to apply those in a very impactful and meaningful way because they're seeing cause and effect as they do it, right?
Right.
They're able to make a change. They're able to count on the way the robot is moving, and it's gonna make that visual and visceral impact to them on, hey, we just made that do that, and that's real to them,
Yep.
right? It's no longer the word problem. They're no longer doing the Johnny has to go 20 miles and that kind of thing. It's actually something they're working with and they're seeing cause and effect.
Right.
Okay, so what are some of the other things that we can actually again talk about this when we start talking about our STEM envelope?
We talk about the technology involved in that servo motor.
Okay, so we got technology involved in that, the creation of this and all the components in the manufacturing process of what does it take to extrude those aluminum beams, that plastic wheel and extrusion
How's that
process.
wheel made?
How's it made? What's it actually composed of?
Why is this a different, in the science side, why is it important that the outside of this wheel be made of a different material than the inside?
Okay, so you can begin to see that if we just look at this in a slightly different way, that we can begin to talk about STEM in a whole new way. I saw a question about lesson plans, and we'll jump ahead a little bit. We're gonna talk about it more later, but there is coming lessons plans for this, right?
Correct. There are some 3-week STEM units that last a 3-week time period that involve multiple activities that students would be involved in that are all STEM activities.
Okay, so that's coming soon. We'll talk more about that a little bit later, but we are going to definitely plan. Again, one of the things I can't emphasize enough is we're going back to feedback that we had from actual teachers that were using Tetrix in the classroom and what they told us they needed to be able to successfully implement this, and that was one of the things as well. We wanted to maximize their time. We wanted to make them feel like they weren't just on their own. We wanted to give them starting activities. And then we wanted to follow up with curriculum. So that's one of the things that we're in the process of doing. So looks like we've got someone saying problem solving, physics in the middle. This is good. This is good stuff, guys. Energy expenditure and distance traveled. So this is all great. Problem solving in the middle. That's great.
You can read that.
I hope everybody can read it. Again, it's kind of some of the tough things of that's why we're trying to verbalize some of this. Slip conditions, friction, and what else do we have there? Mass and acceleration. Yeah, great.
We can tie that problem solving skill and engineering together. A quick building system. So one of the things we can do is we can modify that quickly. Well, we have gears,
right?
So we can pull this servo off and we can make this a gear drive.
Okay.
So now let's give the students a problem to cover a distance in the shortest amount of time.
Awesome. So now again, we begin to bring in some of the simple machine concepts of gearing and then the related math skills that go with that, as far as the gear ratios, how that impacts the performance in a real way.
And one of the things that's very visible, if you put enough gears on this, you can really show that it takes off. It takes a lot of power to get it going, but once it gets going, it gets moving fast.
Right.
And so you can, by adding a gear train, make a little modification, move your battery a little bit, move the servo a little bit, add a gear drive system, talk about gear ratio.
Awesome. So again, this is one of the strengths of this. And I'm going to go outside of this a little bit. Just robotics in the whole. When you start to give a student access to a product or a system that allows them to see immediate cause and effect, where they can make a physical change, and you can ask a question, you can ask them to make a change, and they can make that change, and then see the immediacy of what that change did and the observed behavior. It's just amazing what that does for them. And let's talk about that just for a minute too, because one of the things we sometimes forget to talk about is that when you begin as a teacher to ask them to observe that and then take the opportunity, okay, so let's work on our communication skills. I want you to write up what you and be able to effectively communicate to me what you just observed, what you saw, right. What change did you make, and what effect was it on the behavior. So there's all those aspects as well that you begin to cross over into literacy and things like that impact this as a product.
That would have made English class a lot more interesting.
It would have. It would have. If I had to write a paper about how my robot moved, it would have. Looks like that there's, can we comment on a mechanical strength of Tetrix Prime parts, assuming the needed power supplies available? Well, the aluminum is 7005 aluminum. So it's the same aluminum structure that you've got with the Tetrix Max system. You've got a square tube structure. So with the strength inherent in that specific structure, if you engineer the process properly, then you're really kind of can be amazed at what it actually will do. Now, the thing is that you have to remember your basic engineering principles if you really want to maximize this. I might make a kind of a scaffolding structure or triangles and stuff like that in a grid to really maximize that if I really wanted to use it for strength. But the main thing to remember is the component is there with the strong aluminum background. So gear ratios, torque versus speed. There's all those things that you can begin to talk about, and we're going to go ahead, and we're getting close on time, so we don't want to spend all too much on just the one Wheeliebot. But this has been great comments that you guys are giving us. There are two other robots that we have building instructions with the kit, so that you're not just building the one robot. We've got the BuggyBot.
This BuggyBot, we use two drive motors, so we get differential drive.
Okay.
Let's talk about that a little bit.
Different drive system.
Different drive system. We have the gripper assembly actually that's on this one is actually optional.
Okay.
The teacher would pre-assemble that, so students don't spend a whole lot of time putting that together. It's a one thumb screw attachment to a beam with a wing nut on the bottom, and so it goes together really fast. They can add it on there.
They could add that on the Wheeliebot too.
Add it on the Wheeliebot. It'll fit on any of them. They can with the BuggyBot we add a beam to that gripper with a gear drive, and now we can talk about gear ratio and leverage. And again, we're talking about simple machines.
Yep.
And we can if you engineer that incorrectly, the gripper is almost uncontrollable. It moves so fast.
Yep.
Or you can gear it properly like this one is, and it makes it a much more controllable gripper. And then you can change the length of that beam.
Okay.
And you can talk about leverage and how much higher you can lift, but what you have to give up.
Gotcha.
Trade-offs.
Somebody had a question asking about the plastic gears and how well they hold up against in relationship to aluminum gears. Obviously, plastic is not as durable as aluminum. Everybody knows that. But here's the cool thing. Because we're working with the same geometry, I could actually take my aluminum, if I needed to, I could take my aluminum max gears of the same size, 40 tooth, they're the same size gears. So I've got a 40 tooth prime gear and a 40 tooth max gear. One's made out of plastic, one's made out of aluminum. They're actually interchangeable. I could use them on either system. So if I was in a max build and I needed to really reduce and worry about weight as an issue, I could potentially use the prime plastic gears to reduce my weight and still have a robust gear. On the other hand, if I was with Prime and I needed strength was an issue, we talked about, somebody had a question about the aluminum elements in Prime and how robust they would be. I could potentially use the Max aluminum gears with my Prime robot and have it work just fine. It's just a matter of what's going to work best. And this is why I said at the very beginning, when you talk about this as a system, for those that are experienced with it, you can look at it as a huge assortment of brand new parts that'll work with what you have. And those that are getting it now can look at it the same way. If later on down the line, if I want to expand on this, I can get any of the Max components and they'll work together. So that should hopefully address that question on the gears. Now we've got
about the
we're going to go, then the last robot is the PickyBot.
PickyBot's is stationary. Instead of being a movable robot that moves around, this would be more typical of a robot that might be used in an industrial situation. And again, we use the motors to lift and turn, and we can learn about the geometry of the work envelope. Depending on where the joints are and how those joints are made and how they move, we can look at different relationships or geometry of work envelopes, and we can do some pick and place activities.
Okay. Well, so a lot of things that sometimes we get are kind of stuck in the rut as far as thinking of robots in just one way. So we wanted to really, again, give an example of a robot that wasn't mobile. Sometimes we get I got to build a mobile robot that builds around, but this is actually very representative of a more industrial type of a robot, what we would see in industry in a pick and place type of robot. So that we do give building instructions for that.
Yes.
I saw a comment about the way that they kind of work together, and exactly right. We do want to make sure that everybody understands it is one big family. Tetrix is a one big system, and we are separating this out as a kind of an entry point. Prime, for those of you that aren't exposed to the Max, but it's certainly not, again, it's a starting point, going back to what we started with the process with. Here's a question. Are the new pieces of the Tetrix Prime approved for use for first competitions? They are with limits, and let me go ahead and expand on that. The main and part of the components, the aluminum pieces, the wheels, those type of things, those are part of the Tetrix family, and as such of that, they are allowed in the first competition for FTC specifically. Now, the pre-assembled parts like the gripper and the remote control and the receiver, those, however, are not, because that's an assembled piece that's prefabricated. So that unfortunately didn't fall under their rules. They, by the way, being US First, are the one that set those rules. Pittsco and Tetrix did not, but they said, according to their rules, that the bulk of the Prime system is definitely going to be allowed and usable in the FTC competition. Hope that answered that question. Before we get away, and time has kind of gone faster than what we wanted, we do want to go ahead and just mention, we did talk earlier about the curriculum aspect. We are expecting sometime summer release, Ray, is that correct?
Sometime summer, probably June. We're looking at 2 and possibly 3 curriculum units. The 2 will definitely be out. The third one is we're still working on the design concept of it. We have a curriculum that deals mostly with remote control, and we have a curriculum that deals mostly with the autonomous type robots. And there are 3 weeks of activities in each one of those units that deal with STEM topics, math, science, engineering. That we build some robots, and we do some engineering to change those robots around a little bit, and we do some engineering and math activities with those.
Okay.
So you do a couple 3 days worth of activities to kind of learn the basic concepts, and then there's a lot of open-ended challenges.
Okay. So the idea is that we are going to give the teacher, both the beginner and then also the experienced teacher, some help with coming up with basic curriculum. Yes. and some support from that area of things. So we're getting really close. We want to make sure at the end we've got there are some options for you to kind of follow up with this. hopefully everybody enjoyed the hour. It went a lot quicker than what I thought it was going to. We've got, you can hit our Tetrix Robotics on social media, facebook.com, Tetrix by Pittsco. Hit our Twitter account on twitter.com and Tetrix Robotics. There's YouTube videos that we've got a YouTube channel, Tetrix Robotics.
And as a matter of fact, this the YouTube channel is where we are going to place the recorded webinar, and everyone who registered will get the link to the recorded webinar as well as a PDF of the graphic organizer that we've been using.
Cool. And then the other thing too, we want to encourage everyone, please don't hesitate to visit www.tetrixrobotics.com. We've got at that website, if you haven't been to it in a while, has been revamped late fall. We did that, and we've got videos that we've got posted. We've got a RoboBench video series where we're going to try and expose myself and Ray and other people talk about Tetrix robots and how they work and that type of thing. We've got build suggestions where we're going to post actual instructions on how to build different robots that you've seen. We've got projects, we've got pages on competition, we've got product itself. So please feel free to check that out and let us know what you think. Ruthie, anything else that you want to think of? We can.
I think that's it. We're right on time. We're just 1 minute over. That's pretty good timing.
Okay. Well, we apologize for that 1 minute over. So in the meantime, I hope everybody enjoyed this. And if you did, let us know, and maybe we'll get a chance to do another one of these.
And
Number one fan.
And if you think of something we left out and you need more information on something, get a hold of us. Contact us. Let us know.
Okay. Well, we appreciate everybody, and I think that was my friend Connie from Nebraska, and always appreciate Connie. So good job, and continue to work with the camps, Connie, and we'll be looking forward to hearing from you on how that goes this summer. So again, everybody, thank you. Come back and see us, and enjoy.